I'm going to write the second recursive formula. First of all, I have any questions here? Okay, the second one is the following. So you can write dn as n times dn minus 1 plus minus 1 to the power n for n to greater or equal to 2 integers. That's a bit better because you can start using it starting from n equals to 1. I'm not going to derive this. The derivation of this is in the text. This was also in the book too. This is in the text and it uses this formula. It's not hard, just this time you don't need to do any counts, you just need to do substitution several times repeatedly to get this, right? So let's just do this one. So this is easy to get using 1, which is this formula over there. So again, it can be useful. For instance, you can calculate, I mean, if you know B4, let's say you can calculate B5 as 5 times B4 plus minus 1 to the power 5. Minus 1, this is 44. Question I think where they ask, I don't remember the exact statement. You need to show that this thing is odd when, so it's even when n is odd, something like that, or it's odd when n is even. I think it's clear when n is even this would be odd, right? Because if n is even, then you would have an even number here. So that's a big even number because n is even. And then you would have a plus 1 here because n is even. So even plus 1 would be an odd number. So if n is even, you would get an odd here. Is that correct? Just looking at these formulas, you can answer questions of this type. And the book has questions. So let's do some examples. Okay, so at a party of n men and woman, A, so let's do this way. How many ways A can the woman choose male partners for the first dance? B, how many ways are there for the second dance? If everyone to change partners. Okay, so what do you say?
And factorial for A and
So add factorial for A to begin with. Put the woman in whatever position and man in whatever position, and woman can choose n factorial ways. N factorial ways. Okay, for B,
arrangement
the arrangement
of N.
of n, because you see now that the first dance has happened, I have a natural order of this, let's say male, man, and then now what I need to do is just anything but that order is okay, so I need to look at arrangements of n. Okay. So this is assuming that your starting position is the first dance pairing. All right. Here's another one. This is another head check. So suppose again we have n woman and man. Check head at the restaurant. In how many ways? The heads can be returned so that no one gets the correct head and let's see the answer here. And each man, second case, gets a male head and each woman gets a female head. But no one gets the correct head. Okay, so the answer to A is what we've been talking about, I suppose. This is just arrangements of what? 2n. So this is the answer. And what's our answer in the second case? 2 times the n is 1. Anyone who disagrees?
It's derangement of N squared.
Derangement of n squared. You want to explain?
So it's like you can just look at the men separately, and then you have derangement N ways of doing that, and then for the set of females, you have derangement of N ways to do that as well.
The second one should be fewer than the first one, but because you have a restriction after all, you still want man to get male heads, woman to get female heads. It will be a subset of part A, basically, right? But nonetheless, you have the first distinction. First, you separate the woman heads and the man heads, and then you look at the arrangement separately in each case. So this is indeed dn times dn. For instance, if n is equal to 2 women, 2 men, what do you get? D2n would be 9, and D2 times D2 is 1. 1. So, and that makes sense, right? If you have 2 women heads and 2 male heads, then there is only one way to get the arrangements in. Here, you get only one situation where you can achieve the second one. Whereas for the first one, of course, you have many more situations. Number 15 in the book, I'm going to add a few more parts to it. So we will do first what's in the book and a bit more. Example 3. So this is again the boring head check thing. So we have 7 men, they check heads at the party. In how many ways? The heads can be returned so that so A. Exactly one person, well, this is not the part, this is not from the book, but I'll add it. So exactly one person receives his or her head. Receives the correct head, that's what it is. At least one of the men receives his own head. At least 2 So let's just do these ones and then I'll edit them. So exactly one person receives the correct head. What do you say? So remember what the arrangements of 7 count. If I ask you the question, no one receives the correct head, you would say the 7, right? Now we want exactly one person to get the correct head. And all the rest will get incorrect matches. I want, just in this business, just don't calculate numbers. Tell me them in terms of BN or M factorial, etc. So where do you get 76?
Well, you choose one person out of the 7 to get the right head.
Okay, so that's 7, right? 7 choose 1.
And then times the arrangements of 6.
And then times the arrangements of 6. Right? So this is 7 choose 1, which is the choice, choose the person to get the correct head. And the arrangements of the remaining, which is D6. Now we want at least one of the men to receive the correct head.
7 factorial minus derangement of 7.
So 7 factorial is all permutations, and then we have the count where nobody gets the correct head, so we just subtract this from 7 factorial. And the remaining arrangements, there should be at least one person getting the correct head. At least 2 men receive the correct head.
So 7 factorial minus d7 minus 7d6.
So 7 factorial minus d7. So now we have at least 1. And then minus, you said?
7d6.
7 times d6, right? This is where no one receives correct head. This is where exactly one person. This is everything. So I subtract from this where no one receives, exactly one person receives, so the remaining should be there at least 2 people who will get the correct head. Any questions here? Okay, let's add a few more parts to it. So these 2 parts are parts from the book, and the book in the first part asks you to get the count of no one receives the correct head, which is d7. So included here. So let's continue. Let's have a part D, but before that, let me ask the question, change the question. So what's the probability that, so let's say this is part B, of exactly one man receives his own head. Exactly 5 men receive correct heads. Exactly 6 men receive correct heads. And D is everyone. Okay. So what's the probability that everyone receives the correct head? Let's start with something.
Or just how many ways?
I'm asking for a probability, which is
Okay.
the ratio. So that would be
1 over
1 over n factorial, right? Which is, I'm in this question, so in this case it would be 7 factorial. So out of 7 factorial arrangements, there would be one situation where everyone gets the correct head, one will return the head. Now let's go back to D. Exactly one man receives the correct head, his own head. That should be now simple because we did the count actually in A. So this is the ratio of 76 to 7 factorial. So event that happens is counted here. Probability is that the ratio over all arrangements. Okay. Exactly 5 men receive correct heads.
7 choose 5 D2.
7 choose 5. D2. Which which is 1. So actually, let me write it this way in case we see a similar question. So the probability will be 7 factorial. So what's going on in the numerator here? I'm choosing the 5 people who will receive the correct heads, or 5 numbers which will be fixed in their natural positions. You can think of it in different contexts this way. And the remaining 2 will have to be in consideration. There's only 1 making of it, so this is 1. So this is just 75 divided by 7 factorial. Exactly 6 men receive correct heads.
0.
0.